The evening of October 12, 1944, and Lieutenant Commander Masao Yamaguchi stood on the tarmac at Tainan Air Base, watching the sun sink below the western horizon of Taiwan. Around him, ground crews swarmed over 27 Mitsubishi G-4M bombers, their aluminum fuselages catching the last orange light of day. The mission briefing had been clear. American carriers were operating 60 miles east of the island. They'd been hitting Formosa's airfields for 2 days straight, destroying hangars and fuel dumps with impunity during daylight hours. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But daylight belonged to the Americans. The night would be Japan's. Yamaguchi had led night bombing missions for 8 months, ever since the crushing defeat at the Philippine Sea had forced the Imperial Japanese Navy to abandon daylight operations. The mathematics were brutal but simple. In daytime, American fighters swarmed like hornets, radar-directed combat air patrols, hundreds of Hellcats with experienced pilots. Even the vaunted Betty bomber, with its exceptional range and payload, couldn't survive that gauntlet. The losses were unacceptable. So, the Navy had adapted. Night attacks, low-level approaches, radio silence. The Americans had ruled the day since Midway, but darkness was the great equalizer. You couldn't shoot what you couldn't see. The doctrine made perfect sense to every pilot who'd survived this long in the war. American radar, everyone knew, was good for early warning. The big ground stations could detect formations at 100 miles. But airborne interception? That was different. That required miniaturized equipment, rotating antennae, complex electronics that could function in the vibration and temperature extremes of high-altitude flight. The Americans had tried it early in the war with the Douglas P-70, converting A-20 Havoc light bombers with British radar sets. The results had been underwhelming. Too heavy, too unreliable, too easy to evade. Japanese intelligence assessments from earlier in 1944 had been reassuring. American night fighter capability remained limited. Their radar could detect bombers, yes, but only under ideal conditions, and even then, closing for a kill in darkness required visual contact. The pilot still needed to see his target silhouetted against stars or clouds, or, if you were unlucky, moonlight. On a dark night, with scattered clouds and good piloting, a bomber could slip through undetected. This was the foundation of confidence that carried Yamaguchi and his pilots through their pre-flight checks. They weren't being sent on a suicide mission. This was calculated risk, backed by months of experience. Since June, night bombing raids had achieved reasonable success rates. Some losses, certainly. War demanded sacrifice. But nothing catastrophic. Nothing that suggested the Americans had developed a counter that Japanese planners hadn't anticipated. His co-pilot, Lieutenant Hiroshi Nakamura, was checking fuel calculations. The navigator, Ensign Kenji Tanaka, was plotting their approach route. 3 gunners, teenagers who'd volunteered straight from technical school, were testing their 7.7mm machine guns. The tail gunner's 20mm cannon was the bomber's only real defensive weapon, but it wouldn't matter tonight. They wouldn't be getting into dogfights. The plan was elegant in its simplicity. Take off after full darkness. Fly north over the ocean, well away from American radar coverage. Circle back from the northeast, approaching the carrier task force from an unexpected angle. Drop down to 500 feet above the waves, beneath the effective range of ship-based radar. Locate the carriers visually. The fleet would be visible as darker shapes against the colle, phosphorescent wake and ambient starlight. Climb to attack altitude, 2,000 feet. Release torpedoes or bombs. Scatter in multiple directions. Return home individually, maintaining radio silence. It had worked before. It would work tonight. What Yamaguchi didn't know, what Japanese naval intelligence had failed to discover, was that the technological landscape of aerial warfare had shifted beneath their feet. The Americans he was about to face weren't flying converted light bombers with temperamental British radar. They were flying purpose-built killing machines, designed from the ground up for one mission: Find bombers in total darkness and destroy them. The Northrop P-61 Black Widow had arrived in the Pacific Theater in June of 1944, only 4 months ago, but that was an eternity in wartime equipment cycles. The first units had deployed to Guadalcanal, to Saipan, to newly captured island bases across the Central Pacific. By October, 5 night fighter squadrons were operating Black Widows in the theater. One of those squadrons, the 418th Night Fighter Squadron, was flying cover for Task Force 38 that evening. The P-61 was unlike anything Japan had encountered. Twin-engine, twin-boom design, 3-man crew, pilot, radar operator, and gunner. Powered by 2 Pratt & Whitney R2 800 engines producing 2,000 horsepower each, top speed 366 miles per hour, service ceiling 33,000 feet, range over 500 miles. But the engines and speed were secondary. The real weapon was mounted in the nose, the SCR-720 Airborne Intercept Radar. The SCR-720 was a technological marvel that represented years of development by MIT's Radiation Laboratory. It operated at 10 centimeter wavelength, using a cavity magnetron that generated 50 kilowatts of pulsed microwave power. The antenna was a parabolic dish 29 inches in diameter, spinning at 360 revolutions per minute inside a fiberglass radome. The display showed targets as blips on a circular cathode ray tube, with range indicated by the distance from the center and azimuth by position around the circle. Detection range against a large bomber, 15 miles. That was the number that would have terrified Yamaguchi if he'd known it. 15 miles. A bomber flying at 200 knots covers 15 miles in 4.5 minutes. Plenty of time for a Black Widow to accelerate to intercept speed, climb or descend to match altitude, and close to firing range. And unlike early war radar systems that required ground controllers to vector the fighter onto the target, the SCR-720 allowed the aircraft to hunt independently. The radar operator would call out range and bearing. The pilot would adjust course. The radar operator would refine the approach. At 2,000 feet, visual contact. At 600 feet, open fire with 420mm cannon in the belly. 4.5 minutes from detection to kill. The Japanese had nothing equivalent. Their most advanced airborne radar, the H-6 Model 1 Mark IV Kai, could detect ships at maybe 30 kilometers under optimal conditions. But it was a surface search radar, not designed for air-to-air interception. It was installed on long-range patrol aircraft and flying boats, not fighters. For airborne interception, Japanese night fighters like the Kawanishi Ki-45 relied on ground-controlled intercept, where land-based radar would direct the fighter into the general area of enemy bombers, then the pilot would search visually. This worked, after a fashion, if you were defending your own territory where you had ground radar stations and clear radio communication. It worked less well if you were over open ocean, far from land, where there were no ground controllers, and the night sky was an infinite volume of empty space. The doctrine that had carried Japan through the first months of the war, the assumption that night operations provided inherent safety, was about to collide with a technological reality that Japanese planners had either ignored or failed to comprehend. At 2100 hours local time, Yamaguchi's bomber lifted off from Tainan. 26 others followed at 30-second intervals. They formed up loosely over the ocean, maintaining visual contact through position lights that would be extinguished once they approached the target area. The flight northeast was uneventful. 2 hours of darkness, the engines droning steadily, navigation lights reflecting off scattered clouds. At 23:15, they began their turn south. Time to descend. Time to go dark. On the deck of USS Hornet, 70 miles southeast. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Radar operators on the SK Air Search Set had been tracking the Japanese formation since 2300 hours. They'd watched the bombers fly north, watched them turn south, watched them descend. The data was fed to the Combat Information Center, where it was processed and evaluated. Fighter Direction Officer Lieutenant Commander Paul Henderson studied the plot. 20-plus contacts, approaching from the northeast, altitude decreasing. Classic night bomber profile. He reached for the radio. Moonlight flight, this is Cherokee Base. Vector 350, Buster. Bandits inbound, bearing 330, range 40 miles, altitude descending through 8,000. 400 miles to the northwest, at Isley Field on Saipan. Lieutenant Dale Haberman and his radar operator Lieutenant Raymond Mooney were just returning from a patrol that had yielded nothing but empty sky. They were exhausted, disappointed, ready for the debriefing that would confirm another fruitless night. Neither man knew that their squadron mates, flying from the escort carrier Manila Bay steaming with Task Force 38, were about to write a chapter in aerial warfare that would fundamentally alter Japanese night bombing doctrine. The P-61s climbed into the darkness, their black paint making them nearly invisible against the starfield. The pilots couldn't see the bombers yet. They didn't need to. The radar operators were calling out ranges with mechanical precision. Contact, bearing 342, range 12 miles, altitude 6,000. The radar didn't care about darkness. The radar saw electrons reflecting off aluminum and steel. The radar saw mass and velocity and position. The radar saw everything. Yamaguchi never knew what hit him. One moment he was flying through calm darkness, the ocean invisible below, the horizon marked only by the faint division between black sea and slightly less black sky. The next moment, tracers were streaming past his cockpit from behind and below, 20mm shells punching through the Betty's thin aluminum skin like it was rice paper. The bomber had no armor. Weight savings to maximize range and payload. Self-sealing capability. Cost savings, because Japanese industrial capacity couldn't produce the specialized rubber compounds in quantity. These design decisions had made sense in 1941, when the Betty's range had allowed it to sink the British battleship Prince of Wales and battlecruiser Repulse off Malaya. They made less sense now, when a single burst of cannon fire could ignite those unprotected fuel tanks and turn the bomber into a fireball. Yamaguchi's aircraft exploded at 23:38. The P-61 pilot, Lieutenant Hermann Fleischer, pulled up sharply to avoid the debris field, his radar operator already scanning for the next target. Contact bearing 347, range 8 miles. They weren't hunting one bomber, they were hunting 27. And there were 4 Black Widows in the air. The mathematics were brutal. Each P-61 could engage multiple targets on a single patrol. Radar-guided interception meant no wasted time searching, visually. Once the radar locked on, once the operator called out bearing and range, the kill was almost inevitable. The bombers couldn't see their attacker. They couldn't evade what they couldn't detect. They couldn't defend against an enemy who saw them in total darkness from 10 miles away. By 00:30 on October 13th, 14 of Yamaguchi's 27 bombers had been destroyed. 14, over 50% losses on a single mission. The survivors scattered, abandoning their attack runs, jettisoning ordnance over empty ocean, diving for the deck in desperate attempts to evade the invisible killers. Some made it back to Tainan. 13 aircraft landed before dawn. Crews tumbled out pale and shaking, talking over each other, their stories fragmented and terrifying. They never saw their attackers, not once. Just tracers appearing out of nowhere, then explosions. Bombers ahead of them would suddenly bloom into orange fireballs, lighting the night sky, then falling, burning into the sea. The Americans were using some kind of new weapon, some kind of technology that let them see in darkness. It wasn't possible, and yet it had happened. The after-action report that reached Imperial General Headquarters 2 days later was carefully worded but couldn't disguise the disaster. Night attack on enemy carrier force encountered unexpected defensive capabilities. Losses 52%. Mission effectiveness minimal. Further night operations against this target suspended pending investigation. 52%. 14 bombers and 98 crew members lost. For comparison, Japanese night bombing operations throughout the summer of 1944 had averaged losses around 15%, painful but sustainable. 52% was catastrophic. One more mission like that and the entire unit would cease to exist. Something had changed. The Americans had developed something new, and the Japanese High Command needed to know what it was. An answer would come from an unexpected source, 3 weeks later and 2,000 miles to the south. But the truth, when it arrived, would be worse than anyone in Tokyo had imagined. The wreckage arrived at the Yokosuka Naval Technical Research Facility on November 7, 1944. 3 wooden crates, waterlogged and smelling of salt and aviation fuel, transported under armed guard from Manila. Inside was what remained of a Northrop P-61 Black Widow that had crashed into Manila Bay during a low-level strafing run on October 31st. The pilot hadn't survived. The aircraft had hit the water at nearly 300 miles per hour, disintegrating on impact. But certain components, particularly those mounted in the nose section, had remained relatively intact, and those components were about to provide Japanese engineers with their first detailed look at American airborne intercept radar technology. Commander Toshio Nakajima ran the Navy's radar research section. He was 42 years old, educated at Tokyo Imperial University, with a degree in electrical engineering, and had spent the last 3 years trying to close a technological gap that seemed to widen with each passing month. Japanese radar development had started late, hampered by inter-service rivalry between Army and Navy research groups, limited access to advanced components, and a fundamental misunderstanding of how central electromagnetic detection would become to modern warfare. When Nakajima opened the first crate and saw the parabolic antenna dish, his hands started shaking. The dish was 29 inches in diameter, aluminum construction, precisely machined, with a focal point mount for the feed horn. Behind it, still attached to a twisted frame, was a motor assembly that had rotated the antenna at constant speed. Nakajima had seen rotating antenna systems before. Japanese ground-based radar used similar mechanisms. But this was designed for aircraft installation, which meant it had to be lightweight, vibration-resistant, and capable of functioning at altitude where temperatures could drop to -40 degrees Fahrenheit. The second crate contained the transmitter and receiver units. Western Electric manufacture, according to the stamped labels, Model BC1091. Nakajima spent 20 minutes just staring at the modular construction, the precision of the soldering, the quality of the components. The transmitter used a cavity magnetron, a British invention that Japan had received specifications for via German intelligence channels 2 years earlier. Japanese engineers had built experimental magnetrons, but couldn't produce them reliably at scale. Component quality was inconsistent, vacuum seal failures, frequency drift, power output degradation after 50 hours of operation. This American unit, salvaged from a crashed aircraft, showed hundreds of hours of operational wear and still functioned within specifications when Nakajima's team powered it up using a portable generator. The frequency stability was extraordinary, 10.7 centimeters, plus or minus 0.05 centimeters. Japanese magnetrons at equivalent power levels drifted by 0.2 centimeters or more, which degraded range resolution and made precise tracking nearly impossible. But the real revelation came when Nakajima examined the display system in the third crate. The indicator unit was a plan position indicator, or PPI display. A circular cathode ray tube, 8 inches in diameter, showed radar returns as bright spots on a dark screen. Range was indicated by distance from the center. Bearing was indicated by position around the circle. The display rotated in sync with the antenna, painting a complete picture of the surrounding airspace every 2 seconds. Nakajima had seen similar displays in German technical documents, but seeing photographs was different from holding the actual hardware, from understanding how the circuitry processed the radar returns, from recognizing the sophistication of the signal filtering that eliminated ground clutter and enhanced aircraft targets. He called a meeting of his senior staff that evening. 12 engineers and physicists crowded into the laboratory, standing around the disassembled radar components spread across 3 workbenches. Nakajima didn't waste time on pleasantries. "Gentlemen, we need to understand what we're looking at. This is the radar system that's killing our night bombers." He walked them through the specifications, as his team had measured them. Detection range against a bomber-sized target, 25 kilometers. Maximum range, 40 kilometers. Minimum range, 150 meters. Azimuth coverage, complete 360-degree scan. Elevation coverage, plus or minus 40 degrees from the antenna axis. One of the junior engineers, Lieutenant Saburo Yamada, raised his hand hesitantly. "Commander, those ranges are 3 times better than our best airborne. Set. The H-6 Model 1 achieves maybe 8 kilometers against a surface ship, and that's on a good day with calm seas." "I know," Nakajima said quietly. "And this operates at 10.7 centimeters?" Another engineer, clearly struggling with the implications. "We can't even manufacture magnetrons at that frequency with consistent output." "I know." The signal processing alone, Yamada was examining the receiver unit now, tracing the circuit paths with his finger. "They're using automatic frequency control, phase-locked loop for the local oscillator, logarithmic amplification in the receiver chain. We've theorized about some of these techniques but haven't implemented them. This is years ahead of our development program. Nakajima let them examine the equipment for another hour, let them reach their own conclusions. When they finally fell silent, he asked the question that mattered. How many night bombers have we lost in the last month? Nobody wanted to answer. Finally, Yamada spoke. The official reports say 93 aircraft since October 1st. The official reports are conservative, Nakajima said. The actual number is closer to 140. Do you understand what that means? That's not attrition from combat operations. That's systematic destruction of our night bombing capability by a technology we didn't know existed. The room was silent except for the hum of the generator powering the radar components. We were told, one of the senior engineers said carefully, that American airborne radar was primitive, that it required ground control, that it was ineffective at low altitude. We were told incorrectly, Nakajima replied. Or perhaps American development accelerated faster than our intelligence services could track. Or perhaps, he paused, choosing his words carefully, perhaps we told ourselves what we wanted to believe because the alternative was too difficult to accept. He gestured at the radar components. This system allows an aircraft to detect, track, and intercept bombers in total darkness at ranges where our pilots can't even see their target. The American pilot doesn't need ground control. He doesn't need visual contact until the final attack run. He can hunt independently, over open ocean, with no navigation references except his radar and his instruments. And once he locks onto a target, that target is effectively dead. Can we copy it? Yamada asked. The question hung in the air like smoke. Nakajima looked at the young engineer, saw the hope in his eyes, and felt something break inside him. No, he said simply. We cannot copy this system. We lack the manufacturing capability to produce magnetrons with sufficient power and frequency stability. We lack the precision components for the rotating mechanism. We lack the expertise to replicate the signal processing circuits. Even if we could reverse engineer the design, we would need 18 to 24 months to set up production lines and train manufacturers, and that assumes unlimited resources, no material shortages, no American bombing of our industrial facilities. He picked up the antenna dish, held it so the fluorescent lights reflected off its precisely machined surface. Do you see this aluminum? Aircraft grade, 7075 alloy. We're rationing aluminum for essential aircraft production. Do you see these bearings in the rotation mechanism? Precision ground steel, tolerance of 0.001 inches. Our bearing production is so limited that we're scavenging them from damaged aircraft to repair operational ones. He set the dish down carefully. This isn't a question of copying one piece of equipment. This radar represents an entire industrial and technological ecosystem that we simply don't have. The Americans can build these at scale. They can install them in purpose-built night fighters. They can train crews to use them effectively. They can deploy them across the Pacific Theater. And we cannot respond in kind. Then what do we do? Yamada's voice was barely above a whisper. We adapt, Nakajima said. We stop sending bombers on night missions against targets defended by these radar-equipped fighters. We develop electronic countermeasures if possible. We explore alternative tactics. But most importantly, we stop pretending that darkness provides safety. The Americans have weaponized the night itself, and we are blind men fighting in a world we can no longer see. The report that Nakajima submitted to Naval General Staff on November 15th was 27 pages long, dense with technical specifications and strategic implications. The conclusions were stark. American airborne intercept radar represented a generational leap in technology. Japanese night bombing operations against radar-defended targets were no longer sustainable. Expected loss rates would exceed 60% if operations continued. No countermeasure was available in the short term. Recommended. Action. Suspend night bombing missions, except in situations where tactical necessity outweighed probable losses. The report circulated through various levels of command over the next 3 weeks. Some officers accepted the findings. Others argued that Nakajima was being overly pessimistic, that the high loss rates in October were statistical anomalies, that Japanese crews just needed better training or different tactics. The debate ended on December 12th, when another night bombing mission against American ships supporting the Mindoro landings resulted in 34 of 58 aircraft failing to return. 58% losses. The survivors reported the same terrifying pattern: invisible attackers, tracers appearing from darkness, bombers exploding with no warning. One pilot described flying through a formation and watching aircraft ahead of him detonate one after another, like firecrackers on a string, while never seeing a single enemy fighter. After December 12th, Japanese night bombing operations against American naval forces effectively ceased. Not officially. There was no formal order suspending the missions, but squadron commanders quietly stopped volunteering for night strikes. Mission planners quietly stopped scheduling them. The bombers that had terrorized Allied bases during the first years of the war, flying with impunity under cover of darkness, were grounded by a technology they couldn't see and couldn't counter. The irony was that Japan had pioneered some elements of radar technology. A Japanese engineer, Professor Hidetsugu Yagi, had invented the Yagi antenna in 1926, a directional antenna design that would become fundamental to radar systems worldwide. But the patent had been largely ignored in Japan and exploited by Western researchers. By 1944, American and British radar technology had advanced so far beyond Japanese capabilities that the gap was essentially unbridgeable. The human cost of that technological gap was measured in burning aircraft falling into dark waters. In the 6 months between June and December 1944, Japanese night bombing forces lost approximately 400 aircraft to all causes. Post-war analysis suggests that 60 to 70% of those losses were directly attributable to radar-equipped American night fighters. That's nearly 300 aircraft and over 2,000 trained aircrew, lost not to tactical errors or operational mistakes, but to a fundamental mismatch in technological capability. The crews who flew those missions were among Japan's most experienced aviators. Many had been flying since the early days of the war, survivors of China, the Philippines, the Dutch East Indies. They'd seen the war turn against Japan. They'd watched American industrial might slowly overwhelm Japanese defenses. But they'd believed that skill and courage and tactical adaptability could compensate for material disadvantage. The radar-equipped night fighters proved them wrong. Skill didn't matter if you couldn't see your attacker. Courage didn't matter if enemy technology could detect you 15 miles away in total darkness. Tactical adaptability didn't matter if the fundamental physics of electromagnetic radiation allowed your opponent to hunt you with impunity. Lieutenant Kenji Tanaka was one of the few navigators from Yamaguchi's original squadron who survived the war. In a 1952 interview with American occupation force historians, he described the psychological impact of those night missions in late 1944. "We knew we were going to die," he said, his words translated from Japanese, "not as a probability, but as a certainty. The Americans could see us, and we could not see them. It was like fighting a ghost. You would be flying in formation, maintaining position on your wing leader's navigation lights, and suddenly the aircraft 200 meters ahead would explode. Just explode, bright orange flash, and then falling wreckage. No warning, no defensive fire, just instant death. We tried everything, flying lower, skimming the waves at 50 meters altitude, but the radar could track us even there. We tried flying higher, 8,000 meters, hoping to climb above their intercept ceiling. They climbed faster than we could. We tried scattering, approaching from multiple directions to split their defenses. They simply engaged us one at a time, methodically. By December, we stopped flying night missions against the American fleet, not because we were ordered to stop, but because there was no one left willing to fly them. The veteran crews were dead, the replacement crews had no experience, and all of us, veteran and replacement alike, understood that we were being sent to die for no tactical gain. Tanaka paused in the interview, and the translator noted that he was crying silently. The worst part was knowing it was our own fault. We'd started the war. We'd attacked Pearl Harbor and Singapore and Manila. We'd believed we could defeat America through superior spirit and tactical excellence. And now we were learning that spirit doesn't stop radar waves. Excellence doesn't prevent detection at 20 kilometers range. Technology matters. Industrial capacity matters. And we had neither. The captured radar equipment remained at Yokosuka Naval Technical Research Facility through the end of the war, sitting on workbenches like an accusation. Engineers would occasionally power it up, watch the sweep line rotate on the display, marvel at the precision of components they couldn't replicate. Some tried to sketch modified designs that might be buildable with Japanese industrial capacity. Others simply photographed it from every angle, documenting a technological achievement that represented everything Japan had failed to become. By February of 1945, the strategic situation had deteriorated beyond recognition. American forces had landed on Luzon. The Philippines were falling. The Formosa air bases that had launched those doomed October night raids were under constant bombardment by B-29 superfortresses flying from the Marianas. Japanese air strength throughout the theater was collapsing not just from combat losses, but from the systematic destruction of fuel supplies, spare parts, and trained maintenance personnel. But even in this chaos, the lesson of the radar-equipped night fighters continued to echo through Japanese military planning. When the High Command began organizing for the defense of Okinawa and the home islands, one thing was clear: night operations could no longer be assumed safe. The Americans owned the darkness now. The kamikaze tactics that emerged in the Philippines and intensified at Okinawa were partly a response to this technological reality. If your aircraft couldn't survive long enough to deliver conventional attacks, if radar-guided interception made measured approach and targeting impossible, then perhaps the only option was to turn the aircraft itself into the weapon. Speed and mass and explosive payload delivered in a single instant that gave the defenders no time to react. It was desperation masquerading as doctrine, and it was born, in part, from the recognition that the technological gap had grown too wide to bridge. The Black Widow crews who'd achieved those devastating interception rates in October and November didn't fully understand what they'd accomplished. From their perspective, they were just doing their jobs. The radar showed contacts, they flew intercepts, they shot down bombers. Mission success was measured in confirmed kills, not in strategic paradigm shifts. Lieutenant Dale Haberman, flying from Saipan with the 6th Night Fighter Squadron, ended the war with 4 confirmed kills. His radar operator, Lieutenant Raymond Mooney, shared those victories. They were skilled professionals operating advanced equipment, but they weren't thinking about how their work was rewriting the rules of aerial warfare. They were thinking about survival, about their next patrol, about whether the powdered eggs in the mess hall were edible. Only after the war, when historians began analyzing Japanese records and interviewing survivors, did the full scope of the devastation become clear. The night fighter squadrons in the Pacific had achieved kill ratios that seemed almost impossible. Some P-61 crews recorded 8 or 10 victories without a single loss. Some squadrons went months without losing an aircraft to enemy action. This wasn't because American pilots were inherently superior. Japanese naval aviators early in the war had demonstrated extraordinary skill and tactical competence. This was because technology had created an asymmetric advantage so profound that skill became almost irrelevant. A bomber crew flying a Betty couldn't outfly radar. They couldn't outmaneuver detection at 15 miles. They couldn't improvise, a counter to physics itself. The strategic bombing survey conducted after Japan's surrender included extensive interviews with surviving Japanese air commanders. Vice Admiral Matome Ugaki, who'd commanded air operations in the final months of the war, was blunt in his assessment. American radar capability rendered night operations suicidal. We lost hundreds of experienced crews attempting missions that should have been routine. By early 1945, we had no effective counter to their night fighters. This, more than any other single technological factor, eliminated our ability to conduct offensive air operations. Admiral Ugaki's diary, recovered after the war, included an entry from January 7, 1945, that captured the psychological impact. Another report of night bombers lost. 12 aircraft dispatched, 4 returned. The survivors report no visual contact with enemy fighters, just fire from darkness. Our best crews, our most experienced navigators, gone. We are fighting an enemy we cannot see, cannot touch, cannot defeat. What is courage worth when the enemy possesses weapons we cannot comprehend? The technological disparity extended beyond just the radar itself. The entire system that made the Black Widow effective, the industrial capacity to produce complex electronics at scale, the training pipeline that created competent radar operators, the maintenance infrastructure that kept sophisticated equipment operational in jungle environments, represented an approach to warfare that Japan had never fully embraced. Japanese military culture had traditionally emphasized spirit over material, individual excellence over systematic capability, offensive élan over defensive preparation. These cultural preferences had produced extraordinary tactical successes early in the war, but they'd also led to systematic underinvestment in radar, signals intelligence, defensive fighter tactics, and other technologies that seemed less glamorous than carrier aviation or battleship construction. By 1944, those cultural choices were manifesting as strategic catastrophe. Japan had excellent fighter pilots, but insufficient radar to vector them onto targets. Japan had long-range bombers, but no electronic countermeasures to protect them from interception. Japan had skilled engineers, but inadequate industrial infrastructure to produce advanced components reliably. The Americans, by contrast, had built their entire war effort around systematic technological advantage. Research universities developed new systems. Industrial corporations manufactured them at scale. Training programs taught thousands of technicians to maintain and operate them. Logistics networks delivered spare parts to forward bases. The entire apparatus of American industrial capitalism, redirected toward military production, had created a war machine that overwhelmed opponents through sheer material superiority. The radar-equipped night fighter was just one example of this approach, but it was an illuminating example because it demonstrated how technology could create advantages that no amount of courage or skill could overcome. Japanese bomber crews in October 1944 were brave. They were well-trained, they were flying capable aircraft, and they died in enormous numbers because American engineers at MIT had developed a better magnetron and American factories in California had learned to build precision antenna assemblies. Commander Nakajima's radar research team continued working through the final months of the war, trying desperately to develop countermeasures. They experimented with radar warning receivers that might alert crews to enemy radar emissions. They designed chaff dispensers that could scatter aluminum strips to create false returns. They drafted plans for electronic jammers that could overwhelm American radar frequencies. None of it reached operational service before the surrender. The prototypes worked, after a fashion, in laboratory conditions. But translating laboratory success into fieldable equipment required manufacturing capacity that no longer existed. American bombing had destroyed the factories. Material shortages made component production impossible. The transportation network that might have delivered finished systems to operational units had collapsed. In his final report, dated August 10, 1945, Nakajima wrote, "We now understand American radar capabilities with reasonable precision. We understand the tactical implications. We understand our own technological deficiencies. This understanding arrives too late to affect the war's outcome. Perhaps if we had understood these realities in 1942, we might have made different strategic choices, but history does not permit revision." The surrender came 4 days later. Post-war assessments by American military analysts calculated that radar-equipped night fighters had destroyed approximately 420 Japanese aircraft in the Pacific Theater between June 1944 and August 1945. This represented roughly 12% of Japan's total aircraft losses during that period, achieved by fewer than 300 American night fighter pilots and radar operators. But the strategic impact exceeded the raw numbers. The loss of night bombing capability forced Japanese forces to attempt daylight operations, where losses were even higher. The need to conserve aircraft for the anticipated invasion of the home islands meant that many potential missions were simply never flown. The psychological toll on surviving crews, knowing that darkness no longer provided safety, contributed to declining morale across all aviation units. Some military historians argue that radar-equipped night fighters were one of the war's most decisive technologies, more impactful than any individual weapons system except perhaps the atomic bomb. Others contend that by mid-1944, Japan was already losing the war through industrial attrition, and the night fighters merely accelerated the inevitable. The truth probably lies somewhere between. Technology alone didn't win the Pacific War, but technology created advantages that compounded over time, that limited enemy options, that imposed costs the enemy couldn't sustain. The radar-equipped night fighter was one such advantage, not war-winning by itself, but contributing to an accumulated weight of material superiority that eventually crushed opposition. For the men who'd flown those missions, who'd hunted in darkness and watched bombers explode 15 miles away through the magic of cathode ray tubes and rotating antennas, the historical analysis mattered less than the memories. Lieutenant Hermann Fleischer, who'd shot down Yamaguchi's bomber on October 12th, returned home to Wisconsin after the war. He worked as an electrical engineer. He married, raised 3 children, lived quietly. In a 1987 interview, 43 years after that October night, he reflected on what the radar had meant. "We called it magic eye, sometimes, the radar, because it felt like magic, watching those blips appear on the screen, knowing they represented actual aircraft out there in the darkness. You'd lock onto a target, close the range, and suddenly there it was, a shape against the stars, solid and real. Then you'd fire, and it would explode, clean, clinical, impersonal. I don't think we understood at the time how one-sided it was. We thought we were good pilots, which we were. But really, we were good radar operators flying a platform designed to exploit a technology the enemy didn't have. Skill mattered, sure. But the technology mattered more. Without that radar, we'd have been flying blind just like everyone else before us. Sometimes I think about the Japanese crews we shot down. Young men, probably scared, definitely brave, flying missions they knew were dangerous. They never had a chance, not really. We could see them, and they couldn't see us. That's not fair fight. That's just technology creating an insurmountable advantage. War isn't supposed to be fair, I know, but it still bothers me, knowing we killed men who never even knew we were there until the cannon shells hit. The captured radar equipment at Yokosuka eventually made its way to American technical intelligence teams during the occupation. Specialists examined it, documented how Japanese engineers had analyzed it, read Nakajima's reports. One officer noted in his assessment, Japanese technical understanding of radar principles was sound. Their analysis of our equipment was accurate. Their proposed countermeasures were theoretically valid. They simply lacked the industrial capacity to implement any of it. This was not a failure of intelligence or engineering. This was a failure of industrial capability. That assessment captures something essential about the Pacific War's final phase. Japan understood what it needed to do. Japanese commanders recognized their technological deficiencies. Japanese engineers could design systems that might have countered American advantages. But understanding and ability are different things. You can know exactly what you need to build and still lack the factories, materials, and skilled workers to build it. By October 1944, when Yamaguchi's bombers flew into that radar-guided gauntlet, Japan's industrial capacity had been degraded beyond recovery. 3 years of war had consumed stockpiles, destroyed infrastructure, killed experienced workers. The merchant fleet that might have imported resources lay on the ocean floor, victims of American submarines. The refineries that might have produced aviation fuel were rubble, destroyed by B-29 raids. The electrical grid that might have powered manufacturing had collapsed under systematic bombing. The technological gap wasn't just about radar. It was about everything. Steel production, oil refining, electronics manufacturing, aviation fuel synthesis, precision machining, quality control, training, logistics, maintenance. America had all of these capabilities at scale. Japan had some of them in limited quantities and none reliably. The night fighter was just where that disparity became most visible, most deadly, most undeniable. In daylight, you could argue that losses were due to tactical errors, or numerical disadvantage, or inadequate fighter support. At night, when bombers simply vanished into darkness and never returned, when survivors reported invisible attackers and instantaneous death, the excuse rang hollow. Technology had created an advantage that couldn't be explained away. 73 aircraft from Yamaguchi's air group were lost between October and December 1944. 73. The group had started the period with 85 aircraft. By year's end, it was no longer combat effective. The survivors were reassigned to training duties or transferred to defense of the home islands, where they might face different threats, but at least wouldn't be sent on suicide missions against radar-defended fleets. Other air groups suffered similar fates. The aggregate loss rate for Japanese night bombing operations against American naval forces during the last quarter of 1944 exceeded 58%. For comparison, Bomber Command over Germany, during the worst periods of the night bombing campaign, experienced loss rates around 5%. Double that was considered unsustainable. Japanese losses were 10 times the unsustainable threshold. You can't maintain operations at those loss rates. You can't replace crews fast enough. You can't preserve morale. You can't accomplish tactical objectives when more than half your force doesn't return. So operations stop, not through explicit order, but through implicit recognition that continuation equals annihilation. The bitter irony is that Japan had entered the war believing that technological advantage was secondary to warrior spirit. The myth of Yamato Damashi, the Japanese fighting spirit, suggested that courage and determination could overcome material disadvantages. Early successes seemed to validate this belief. Japanese forces had defeated larger, better-equipped opponents through tactical excellence and aggressive action. But those early opponents, China, colonial forces in Southeast Asia, initially surprised Allied garrisons, hadn't possessed overwhelming technological superiority. Once Japan faced an enemy that combined numerical advantage with systematic technical superiority, the myth collapsed. Spirit couldn't detect radar waves. Courage couldn't stop homing signals. Determination couldn't overcome a 15-mile detection range disadvantage. The lesson was learned at enormous cost, written in the wreckage of 400 bombers scattered across the Pacific floor. Written in the names of 3,000 aircrew who died fighting an enemy they never saw. Written in the despair of commanders who sent men on missions they knew were hopeless but felt compelled to execute anyway. Commander Nakajima survived the war. He lived until 1976, working after the surrender in Japan's civilian electronics industry. He contributed to the development of commercial radar systems for maritime navigation and air traffic control. In private conversations late in life, he reportedly told former colleagues that he couldn't look at radar equipment without remembering those disassembled Black Widow components on his workbench, the precision he couldn't match, the capability he couldn't counter. "We were children," he said once, according to a colleague's memoirs, "playing with toys we didn't understand, fighting a war we'd already lost but were too proud to acknowledge." The radar was just the clearest proof. We could see the technology. We could measure it. We could understand exactly how far behind we'd fallen. And there was nothing we could do except watch our boys die. The P-61 Black Widow remained in American service until 1954, eventually replaced by jet-powered designs. The SCR-720 radar was superseded by newer systems with longer range and better resolution. Technology continued advancing, as technology does, and the innovations that had seemed so revolutionary in 1944 became obsolete within a decade. But the fundamental lesson endured. Technology matters. Industrial capacity matters. The ability to turn scientific knowledge into deployable systems at scale matters. Wars are won by nations that understand this reality and lost by nations that don't. Japan learned that lesson in fire and darkness over the Pacific, one exploding bomber at a time, throughout the autumn of 1944. The lesson came too late to change the war's outcome, but not too late to shape the nation's post-war development. Japan's remarkable economic recovery and technological advancement in the decades after 1945 drew directly from the recognition of what had been missing: the electronics industry, the precision manufacturing, the quality control, the systematic approach to research and development. The Japan that built the world's most advanced consumer electronics in the 1970s and 80s was, in some sense, responding to the humiliation of captured radar equipment that couldn't be replicated in 1944. National trauma can motivate transformation if the lessons are learned and internalized. Back on that October evening when Lieutenant Commander Yamaguchi had stood on the tarmac watching the sun set, he'd believed darkness would protect him. He'd believed that night operations offered safety, that the Americans couldn't intercept what they couldn't see, that courage and skill would be enough. He was wrong about all of it, and he died never knowing why, never, understanding that invisible radio waves had painted his aircraft on a cathode ray tube 15 miles away, never comprehending that technology had rendered his courage irrelevant. That's perhaps the most profound tragedy of the story, not just that men died, because men always die in war, but that they died fighting a battle they'd already lost before they took off, killed by a weapon they didn't know existed, victims of a technological gap they couldn't see and their commanders refused to acknowledge until the evidence became overwhelming. By the time Japan truly understood American radar capabilities, by the time Nakajima's team had analyzed the captured equipment and documented the implications, the war had entered its final phase. The knowledge came too late for counter-development, too late for tactical adaptation, too late even for effective despair. It simply confirmed what operational results had already demonstrated, that darkness no longer protected anyone, that night had been weaponized, that the entire foundation of Japanese night-bombing doctrine had been rendered obsolete by advances they'd failed to match. 420 aircraft destroyed, 3,000 aircrew killed, an entire operational capability eliminated, all because a laboratory in Massachusetts had developed a better magnetron, and because American industry could manufacture precision antenna assemblies, and because radar operators could be trained to interpret cathode ray displays in time to vector fighters onto targets. Technology had won, Industry had won. Systematic development of material advantage had won. And warrior spirit, tactical excellence, and courage under fire had proven insufficient against an enemy that could see in darkness from 15 miles away. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.